This digital file is cataloged under the title Advanced Arithmetic, but scrolling through its opening sequence reveals an immediate problem. There are no numbers, no equations, and no math. Instead, the file contains page after page of blank space, paper texture, and silence. The only readable data point preceding this void is this single isolated frame. These files represent the raw, unedited output of an industrial-scale mass digitization pipeline. To understand the architecture of modern digital preservation, we have to deconstruct why an arithmetic book containing 25 pages of nothing is the perfect structural artifact. In rigorous digital archiving, empty space is highly intentional data. Consumer algorithms are engineered to strip out null values. A smartphone camera or a basic PDF scanner typically compresses and deletes blank space to save bandwidth. Archival networks operate under the mandate of the digital twin, the requirement that the resulting file reflect the physical and spatial reality of the original object, including every empty page and dimension. Automated systems are explicitly coded to reject pure data efficiency in favor of this physical fidelity. That protocol originates here, in the physical hardware environments where technicians process millions of bound volumes. Parsing the logic of a file packed with empty pages requires reverse engineering the algorithmic decisions made by the equipment that captured it. We begin by analyzing the single graphic asset that precedes the blank files. Looking past its aesthetic design, we examine this bookplate's systemic function. It operates as visual provenance, an embedded, unforgeable metadata tag. Before text extraction occurs, the pipeline reads these markers as a signature, validating the source object's chain of custody. Mass digitization pipelines rely on these front matter artifacts to lock in an origin point before OCR activates. That digital tag anchors the data to this physical institution. A single verified scan of a bookplate establishes the baseline of trust for the thousands of data points that follow it. With the origin verified, the system encounters the subsequent anomaly, 25 blank files. At this stage, the pipeline deploys optical character recognition, or OCR, evaluating the raw visual inputs to extract usable text. As the OCR engine processes one of these artifacts, it scans the image, searching the pixel grid for high-contrast clusters that indicate letters or numbers. Finding no relevant clusters, the algorithm returns a 0, a null text value. This null data is the result of hardware mechanics. Automated scanning rigs physically turn the book's front matter, the protective end papers preceding a title page. The page-turning hardware is indiscriminate, capturing a frame for every single physical sheet it moves past the lens. The algorithm registers a mathematical 0 for text, but that computational result does not invalidate the structural existence of the paper in the scanning cradle. This creates a direct conflict in systems engineering. If the processing algorithm identifies these pages as empty, keeping them requires explicit justification. Deleting these files actively destroys the digitized object's spatial integrity. The digital twin protocol demands a 1-to-1 ratio. Every physical page turn must have a corresponding digital file to preserve the sequence of the bound artifact. The technical trade-off is significant. Archival networks accept vastly higher server costs across millions of volumes solely to host empty space. Allowing an algorithm to automatically delete files it considers empty risks data loss. An OCR system could mistake faded historical ink or a faint pencil diagram for a blank page. Preserving gigabytes of null data worldwide is a deliberate defensive architecture. It ensures no algorithm can subjectively interfere with the historical record. Pulling back from the mechanical pipeline, we can observe the final output of this architecture. The goal is virtualization, replicating a physical object in a three-dimensional digital space rather than just extracting its script. When we digitally reconstruct the book using the raw output, the components lock into geometric parity with the real-world volume. This solid, unbroken sequence of blank files confirms that the scanning hardware operated continuously without skipping a physical sheet. These 25 blank pages provide the proof of a high-fidelity capture. An intact structural sequence is the hallmark of trustworthy archival data. The principles demonstrated by this arithmetic book scale out to the largest preservation efforts in the world. Absolute physical truth must override data efficiency. Excising the empty spaces from an archive irreversibly damages the context of the data that survives. Translating millions of physical texts into a digital archive requires enforcing the physical constraints of reality upon the resulting data. Archival systems are explicitly designed to carry the weight of null data. To accurately map history, preserving the space where nothing happens is as critical as preserving the signal.